second section we're going to look at, our second part of the first section, 8.5, part 2. So we started to talk about this new notation, okay, where you put two numbers and you put angle brackets, and that's how you can represent a vector without drawing. Well, it's one way you can do it. So I wanted to just give you an example of two vectors. This is vector v, and this is vector w. Those are just the names of the two vectors. Remember, when you name a vector, there are two ways to do it. You can either use a bold letter. That way we know if it's bold, it's not a variable. Bold is a vector. Or you can just use a regular letter and put like an arrow on top. Okay, you see in the homework most of the time they use the bold letter. So, what does it mean for two vectors to be equal to each other? Well, let's look at this. Let's say that I drew something that starts here, stops here. And then I draw something that starts here and stops there. Are those two vectors, well, do you think they're equal to each other?
Yeah.
How come?
Same like dimensions, they both go over and up the same.
They both go over and up the same, and that's all that has to be true for vectors to be equal. They do not have to start and stop at the same points. Okay. This one has a different start point than this one, and it has a different stop point. But you still go over 4 and up 2, over 4 and up 2. So for two vectors to be equal, their components have to be equal, not the starting, not the starting and stopping points. Okay, any questions on that idea? Some people think they have to be like right on top of each other to be equal. No, they just have to go over and up the same amount. All right, now I want to go back to that page for a second and try one other thing. What if I did this? Is that vector equal to the other two?
No.
No, that one's not. What about the vector is equal to the other two? The magnitude, yes. It has the same magnitude, but it has the opposite direction, yes. So this one is not the same as the other two, okay? All right, so the last notation I'm going to show you for a vector, this is the one that we use most often. Okay, and it's called unit vector notation. It's pretty similar to the notation I showed you yesterday. First, can someone remind me, if you have a unit vector, we talked about that yesterday, it has a certain length. What's the length of a unit vector? Yep, 1. Yep, 1. So to write a vector in what's called unit vector notation, I'm going to show you two special unit vectors. The first one is I. So if you want to name a vector, you cannot use the letter I to name a vector. You can use V, W, A, B, C. You can use all other kinds of letters, but you cannot use an I, because I is something special. I is a unit vector that points to the right. It has nothing to do with like an imaginary I. Okay. But I is a unit vector, and it points to the right. And it looks just like that. That's a picture of what I looks like. And there's one other special vector, and that one is J. So if you see a bold J, that is defined to be a unit vector that points up. So I and J are two letters you can't use when you're naming vectors because they mean something else. Okay, so J is a unit vector and it points up. That's a picture of what J looks like. It's a unit vector pointing up. And what we're basically going to do is we're going to take i's and j's and we're going to stack them together to build a vector. Okay, think of I and j as like our basic building blocks. We can stack as many of them as we need to build whatever kind of vector we want. Okay. And if we want to sketch like something longer than I, well, we can stack multiple i's together and multiple j's. Right, let me show you how it works. Okay. Let's write the vector 3, 4, but this time we're going to use unit vector notation. I'm not going to start at the origin because if I start there, I'm going to have to draw on top of the axis and then it's hard to see. So I'm just going to start up in quadrant 1. If I start there, how many units to the right do I go? And then how many units up do I go?
3 to the right, 4 up.
3 to the right and 4 up. 4 up. Okay. So there's a picture of the vector 3, 4. Now we're going to build that vectors with I and j's. So let's start with the i's. I'll zoom in a little bit. How many of these vectors do you need to stack together? If you start here
Oh, 4.
and try to start getting yourself lined up with this. 3. Yep. So you're going to take 3 of those and stack them all together. So that's 1, 2, and 3. So what do you think you would call this bottom thing?
3i.
It's 3i. Yep. That's the first part. So we have 3i, and we're going to stack some more on the end. Okay, I'm just going to draw them because that's quicker. How many of the j's would you need to stack up?
4.
Yeah. 4. 1, 2, 3, 4. So now, what do you think you would call that part on the right? 4j. And that's how you write that vector as a unit vector notation. Okay, it's 3i plus 4j. And that's the notation we'll probably use most of the time, okay, going forward. All right, so all you really have to do to write it in unit vector notation is take the 2 numbers you already have, get rid of the angle brackets and the comma, put an I after the first number and a j after the second number. And that's called unit vector notation. All right, now, what if you had something like this? Let's start with like how many i's you would stack together. Okay, how many i's do you need?
2.
Yeah, you only need 2. 1, 2. So it's 2i. Now the problem is j brings you in what direction? Up. We don't want to go up. So what are we going to have to do to j? Yeah, make it negative. And how many of those would we need?
3.
Yeah. 1, 2, 3. And what do you think you call that part? Negative 3j. Yep. So by making I positive and negative, you can basically travel in any directions you need to. Up, down, left, and right. And if you need to travel half a block, you could do 1/2, something like that. Any question on that one? Yeah.
Is that why when looping in computers they use I and J?
When looping, I don't know why those are just common variables they use for counters, but I don't know if it really has anything to do with the fact that that's what they're named here. I wouldn't think so.
You're counting the amount of vectors, so I kind of
Right.
similar.
You are counting, so yeah, I don't know. I guess it could be, but I'm not sure. Yeah. Okay, so let's look at some formulas. So in these formulas, I gotta just kind of say a couple things first. I'm gonna use the letters V and W. Those represent vectors. Okay, alpha represents a scalar. Now remember, we talked about scalars yesterday. When you scale a vector, three things can happen to it. Did anybody remember one of the things?
It can get longer.
Can get longer. Another thing that could happen is get shorter. And one of them, yeah?
And reverse.
Right, if it was a negative scalar, it can reverse the direction. Yep. Okay, so here's my two vectors. Vector V has a horizontal and a vertical component, and so does vector W. When we do an actual problem, those x1 and y1, it's going to look more like this. I'll give you numbers. Okay. Oops. It's B, W. So what we're going to basically look at is everything that we did yesterday, but we're not going to draw any of it. We're going to add vectors, subtract vectors, and we're going to scale them without drawing anything out. All right, let's start with adding. If you have two vectors and you want to add them together, okay, the old way of doing it, if you had one like this, and then you had one like that, was to take the red one, put it on the end of the black one, and then draw the diagonal. Well, if you don't want to draw it, all you have to do is take your two vectors, take the two horizontal components, add them up, take the two vertical components, add them up, and that's your answer. It's not a picture, but it's still the answer that would represent the picture that we did yesterday. Okay, what do you think the difference would be with V minus W? Yeah, all you're going to do if it's V minus W, you're going to take the x component of V minus the x component of W, and then do the same thing for the y's. Yep. So remember, for subtraction, yesterday what we had to do, we had to take the second vector, we had to flip it around, and then add it. That's how we did subtraction visually. Now we're just doing it with numbers. Okay, this is a scalar product. So like it could be 3V or 5V, okay, but this would be a number. That's the symbol your book uses, so that's what I used. So does anyone have a guess? Like, let's say I wanted to figure out what triple a vector would be. Instead of V, I want 3V. Does anyone have a guess what you would do with the 3 and the stuff that you have right there?
Distribute x1.
Yep. It's basically like distributing it. Okay, that's exactly what you do. So you take whatever number is in front, 2, 3, whatever it is, and you distribute it to each component. Yep. All right, and the last thing is this symbol with the double bars. Okay, we did talk about that yesterday. Does anybody remember what those double bars mean? Yes, it means magnitude. Now let's go back I'm going to go back to the page where we just drew vectors because I think this will actually help us a lot. If we want to find the length of this in green, how do you think we would basically do it?
Pythagorean theorem.
Yeah, you do Pythagorean theorem. You take the horizontal number, you square it, take the vertical number, square it, and that's basically like doing Pythagorean theorem. Okay? So you'd have to add them up, 9 plus 16, and then take the square root, which would give you, in this case, give you 5. So that's how you find the magnitude of a vector. You use the Pythagorean theorem with 2 numbers for your vector. Okay, so take each number, square them, add them up, and then when you're done, you take the square root. So this gives us 4 things that we can do with vectors now that we don't have to sketch. Add, subtract, scale, and find the magnitude. Yeah, and not having to sketch it, that's nice, okay, because sketching takes a while. I think sketching's okay if you got a word problem, that'll help. But other than that, there's no reason to sketch to do any of this stuff. Only if you're just starting vectors and you're really trying to understand how they work. But not really beyond that. Okay, does everybody have those 4 formulas? I'll leave them up there. Okay, so let's try each one of these formulas, but let's use some actual numbers. Yeah, I've written the vector each notation. Okay. The first one, this is unit vector. And the other one in the angle brackets is what we learned yesterday. Okay, so first thing I want to do is add these 2 vectors up. And I don't want to draw. I don't want to draw anything. Okay, I just want to add them up. Okay, if you add V and W, let's do it as a unit vector first, and then we can do it the other way after. What would be the I component when you add them up? 5. Yep, 5i. So that means you're taking 5 of the vectors that point to the right, stacking those together. And what would be the j component? Negative 1j. 3 plus negative 4. So you can put negative 1j, or you could just put negative j. So you've got 5 to the right, and then a negative j is which direction? Down 1. That's what it would look like. Okay, how would you write that in that notation? Right. If you're going to write it this way, you do need to put the number negative 1. If you write it in the ij notation, you don't need to put the negative 1 in front of the j. Okay, so that's adding. Any question on that? All right, so let's do subtracting. So now we got b minus w. All right, let's start with the I component. What would be the I component if we subtract these? Negative I. Yep. So negative I. And the j component.
7j?
7j, because it's 3 minus negative 4. And in the notation we learned yesterday, what would that look like? Yep, good. Negative 1, 7. Let's try this one. 3v. This time you don't need w. Okay, we're not We're not using W at all. So what would vector V be if you triple? It's like you're going to stack 3 of them together.
6i
Yep, 6i
plus 9j.
plus 9j. Yep. 6i plus 9j. Or if you want to write it this way, 6, 9. All right. Now, if we look at all our answers, this one, and this one. All those things I circled in red, what are they? They're what? They're what? They're vectors, yes. So when you add, subtract, or scale, the answer you get is a vector. How about here? When you find the magnitude is really giving you the, what do we call that? It's the length. Is length a vector? No, length is a single number. 5, 6, 2.5, whatever it is. So the answer to this problem is not a vector. It's just a number for how long the vector is. All right. So, anyone think they can give me the formula I'm going to use to get the length?
2 squared plus 3 squared.
2 squared plus 3 squared.
And then square root is whatever.
And then square root it. Yep. Okay, so that's going to be the square root of how much? 13. Yep. If they ask you for a decimal, you can round. You can type it in and round it. Otherwise, I just leave it like that. Okay. Any question on? Okay. All right, so let's look at this. So what I have is just a reminder about what a unit vector is. So it says if a vector has a length of 1, magnitude of 1, that makes it a unit vector. What I want to do is figure out what can you do to a vector to make it a unit vector if it's not. Okay. So what I'm trying to figure out is if you have a vector that's too big, I want to know what I could scale it by to make it smaller and make it 1 unit. Or if I have a vector that's too small, what could I scale it by to make it a little bigger so it's exactly 1 unit? So let's look at some different lengths and see if we notice a pattern of what you scale it by to turn it into a unit vector. So let's say you had a vector that was 5 units long. I want to know what I would have to scale it by to make it a unit vector. Yep.
1/5.
1/5. Yep. Let's say we had a vector 8 units long.
1/8.
You'd scale it by 1/8. Let's say we had a vector that was half a unit.
2.
You'd have to scale it by 2. Now, let's see if we can kind of generalize it and see what the pattern is. What if I had a vector that was x units long?
If x is less than 1, it's x. And if x is greater than 1, it's 1x.
1 over x.
1 over x. Yeah. So if you notice, what you scaled by each time was the length flipped. 1/5, 1/8, 2. In this case, x, 1 over x. So it's always the length flipped. That's what you scale by. Okay. So to find a unit vector, if I give you a vector, you're just finding a new vector. You're not changing which way it points. You're just making it a little longer or a little shorter so it's exactly 1 unit long. And the formula is to scale the vector by 1 over its length, the reciprocal of its length. And we figured that out just by looking at the pattern in that chart. It's always the length flipped. And what's the fancy word we use for length?
Magnitude.
Magnitude. Yep. So let's say you had a vector v, and you want to turn it into a unit vector. You would take the vector itself, and you would divide it by its magnitude. That's how you find a unit vector. Take the vector and divide it by its magnitude, which is the same thing that someone else just said. Multiply by 1 over the reciprocal. That's the same thing. Okay, so divide the vector by its magnitude or multiply it by 1 over its magnitude, the reciprocal of its length. That's the formula for finding a unit vector. That's basically what I just wrote. So don't worry about that. We wrote it over there. Now, if you have a vector and it already is a length of 1, then you don't have to do anything. You're good. It's a unit vector. Okay? If it doesn't have a length of 1, and it says to make it a unit vector, then you have to fix it. So let's try using that formula to make a unit vector. Okay, so here's our vector. 3, negative 4. First thing you should do is figure out, did they already give you a unit vector? If they did, then you can just write down the same answer as what they gave you in the question. All right, so if I start at the origin, how many units, bless you, how many units to the right do I go?
3.
So 3 to the right. And then how many up or down?
4 units down.
Yep, down, and how many? 4. 1, 2, 3, 4. So right about there. So if you make a triangle, those are the 2 sides. Did they give me something that already has a length of 1?
No.
No. They gave me something that has a length of what? 5. So what would I scale this vector by to force it to be 1 unit long if right now it's 5?
1/5.
Scale it by 1/5. So we're going to do 1/5 of my vector. And all that's going to do is make it 5 times shorter. And that's what we want. What's going to be my new horizontal if I distribute that out? What is it?
0.
Yep, 3/5. And my new vertical?
Negative 4/5.
Yep. So that's a unit vector, points exactly the same way as the original, except now it's 5 times shorter. Yeah.
What's the point of turning it into a unit vector?
So the next thing we're going to look at, not today, but let's say we had 2 vectors like that, and we want to figure out the angle between them. If all you care about is the angle, it doesn't matter how long you make these vectors. So why not shorten them up so you can work with something a lot smaller, and it's still going to give you the same answer for that angle between them. It might just be easier to work with something shorter. and working with something that's 1 unit long, that's always the easiest case because the number 1 is very easy to do arithmetic with. Yep. But other than that, I don't really know another case where you'd want to do that. Yeah. Okay. Any other questions on that one? Okay. So that's how you find a unit vector. The last 2 things we're going to look at are applications. Okay, we kind of talked a little bit about this one yesterday, using a vector to represent like something moving. Okay, and I think I probably showed you guys the airplane website. So if you use a vector to represent something moving, that's called a velocity vector. It's describing 2 things: the direction the object is moving and the speed of the object. Okay, so when they give you a velocity problem, they're going to give you 2 pieces of information. They're usually going to say, like, let's say you had something moving at 30 miles per hour. Okay, we're going to do a problem in a minute. I'm just making this up. You got something moving at 30 miles an hour, and it's moving at an angle of, let's say, 45 degrees. It means it's kind of like going northeast. That's the direction. Now, when we write vectors, is there an angle in either one of those spots? No. Vectors don't have angles written here. The first number, what does that represent?
X.
Yeah, x, and that's your which direction? This is your horizontal. And the second number represents your what? It represents your y, which is your vertical. So if you're telling me something's moving at a 45-degree angle, I can't think of it as going at a 45-degree angle. I need to think of it as a horizontal and a vertical. Kind of like this picture right here. I can't think of it as this vector in green. I need to think of it as 3i and 4j. So that's what we have to figure out. When they give you an angle and they tell you how long the green one is, you've got to figure out these other 2 sides of the triangle, because that's how vectors work. Vectors don't ever use the hypotenuse. They use the base and they use the height. Vertical, horizontal. So let's, actually I could just use that picture right here. What was the speed I said? 30 miles an hour?
30.
Okay. So that's the length of the green. We'll call it 30. And what was the angle I said?
45 degrees.
Okay, so that's not exactly drawn to scale. Okay, so let's call this bottom side. Temporarily, that'll be my horizontal. We'll call it x. This is my vertical. I'm going to call it y. Let's start with x. I want to figure out how long x is based on this angle and that side. What side is x relative to 45?
Adjacent.
It's the adjacent side. And what side is 30?
Hypotenuse.
It's the hypotenuse. What trig function has adjacent and hypotenuse in it? Cosine. So the cosine, and I'm not even going to use 45. I'm going to do it generically. I'm just going to call it my angle. So the cosine of my angle equals what side is adjacent?
Or X.
X over And in general, not specific in this problem, what side always goes in the bottom? And what about the hypotenuse? Like the color of the hypotenuse, what's the, like how heavy it is?
The quantity?
It is a number, but what does the number in the bottom specifically represent?
30 miles per hour.
But I'm thinking in general. So when you write adjacent over hypotenuse, what do you write? Like, what about the adjacent and what about the hypotenuse? The length of them, yes. Or when we talk about vectors, we don't call it the length of the vector, we call it the magnitude, exactly. The magnitude of, let's just call that green vector V. That's the formula that we set up. That's how you find the x. It's the length of the red side divided by the length of the green side. But we don't call it length, we call it magnitude. And what if you got x by itself? What would be in that box?
Cosine theta times magnitude of V.
Magnitude of V, cosine theta. In this particular problem, it would be 30 cosine 45. That's how you find the length of the bottom. 30 cosine 45. All right, now let's do the same thing for the y. Okay, so now focus on what I'm circling in blue. Okay, just look at the three things circled in blue. What side is y relative to 45? Yes?
Is the x value we just found the number of i's or the magnitude of x?
That's the same thing.
Oh.
It's the same. This is like, 20i or whatever it comes out to. Or, yeah. Yeah, it's the magnitude of this side, which is the number of i's. Now we're going to find the number of j's. Yep, so somebody just said it. What side is this?
Opposite.
Opposite. What trig function involves opposite in hypotenuse? Sine. So the sine of, in this case you use 45, but in general, whatever your angle is. Sine of your angle equals, and what's the definition of sine?
Opposite over hypotenuse.
Opposite over hypotenuse. So y over, and what about the hypotenuse?
The length.
The length, which we call
Magnitude.
the magnitude of it. Yep. So it's y over the length of the hypotenuse. Opposite over hypotenuse. Okay. So now, what would the vertical component be?
The hypotenuse times sine theta.
And okay, so tell me exactly what to put in this box.
Magnitude times the sine theta.
Magnitude.
Sine theta.
Anything else?
The hypotenuse. I don't think so. Oh, well. You need the little v in there.
Yeah, the magnitude of v. Magnitude of v. Which in this case would be 30. All right, so let's just put those together so they look like a vector. Okay, so I'm just going to put it here. So the formula for velocity vector. It is magnitude v cosine theta comma magnitude v sine theta. All right, just to be clear what those two things are. Magnitude v, that's the speed of whatever, the speed of the object in the problem. And theta, that's a Greek letter, and usually we use Greek letters to represent angles. That's the angle. So like if you threw something at 90 degrees, that's straight up. 0 degrees would be like horizontal. 180 would be south. So it's like traveling down. So theta is angle. And that's the formula for a velocity vector. And these two things are always given to you. So all you have to do is take those and just plug them in. So you can see kind of how we're wrapping up trig here, right? We're at the last section of trig, but we're still using the basic right triangle stuff we learned way back at the beginning, breaking it down into like the base and the height of a triangle. Tons of stuff we do is just all about base and height of a triangle. That's it. All right. So I gave you guys the formula already. We did that. Okay. So let's try this one. So we're throwing an object at 50 miles an hour, but at an angle of 30 degrees. I want to write that as a unit vector. And then once I get the unit vector, explain what each component means in this problem. Okay, so you're going to get numbers. And the numbers have a meaning in like real life if you were to do this. Like it tells you something. Okay, but the first step is find the velocity vector. What's my formula to find the x, or the horizontal part of the vector? Just in general. You don't even have to fill in the numbers yet.
Magnitude of V cos theta.
Magnitude of V cosine theta. Yep.
Speed cosine theta.
So it's the speed times the cosine theta. What's the speed in this one? 50.
When we start to do this,
And what's the angle?
30 degrees.
30 degrees. Okay, so we have to figure that out. And then what's the formula to find the vertical?
Speed sine theta.
So the speed, or the magnitude of the vector, which is 50 units, times the sine of the angle. Okay, so let's type that in and see what we get. What should I check first once my calculator comes up? Yeah, so mine always goes back to radians, so put it in degrees. And this is pretty much the only thing today we need a calculator for. So 50 cosine 30. 43.3. So 43.3, comma. And then 50 sine 30 is 25. Yeah, 25. Because the sine of 30 is a half. So it's just half of 50. Okay. So there's our answer in the notation we learned yesterday. How would you write this in the notation we learned today?
43.3i plus
43.3i. Yep. Plus what?
25j.
Plus 25j. Okay, either answer is correct. Just a matter of if they tell you a certain way to do it. Now what? The first number in a vector is always your what? Right, this is your horizontal. And the second number is your vertical. And this problem is about the speeds. So What do you think this 43.3 is? In terms of this object actually traveling at 50 miles an hour at an angle of 30 degrees, yeah?
Distance?
We could figure out distance from it, but it's not distance. It's not a distance.
How far moved right?
Well, movement is a distance. It's not a distance.
Velocity?
It is. What part of the velocity?
How many miles it moves per hour?
Well, it is miles per hour, but
So
what is this? It is 43.3 miles per hour. But I'm looking to what does that mean in this problem? Because it's traveling at 50 miles an hour at an angle of 30 degrees. So,
Forward force?
no, not a force. It is a speed. But yeah,
it's horizontal component.
it's the horizontal speed of the object. What does that really mean? That means if you were standing across the room and somebody threw this at you at 50 miles an hour at an angle of 30 degrees, and you pointed a radar gun straight at the ball, it's coming at you at 43.3 miles per hour. It's not coming at you at 50 because part of that energy is going up, okay, and part of it is pushing it forward. If somebody threw it at a 0 degree angle, okay, like a line drive, like zero degree angle, then it would be coming at you at 50 miles an hour. Okay, but that's its horizontal speed.
Oh, so that's an image of baseballs.
And what do you think the 25 is?
The vertical speed.
That's the vertical speed. So now, if you did the same thing, like threw an object at a 30 degree angle at 50 miles an hour, and you were above it, like in a helicopter, and you pointed a radar gun down at the ball would be coming up at 25 miles an hour. And it would only be going 25 miles an hour the second it leaves your hand, because once it leaves your hand, gravity is going to slow it down and bring it back down. So that's the fastest it would ever go, right when it leaves your hand, 25 miles an hour. Okay? So that's why when people throw an object and they want to get it somewhere quick, as long as there's nothing in the way, they throw it pretty much horizontal, because then all the energy is going to bring it forward. They don't throw it straight up in the air if they want to get it forward quickly. So most of the energy is going forward, but there is some going up because it's a 30 degree angle. Does someone have a question?
I had a weird question, but isn't that 3D and you say we're only doing 2D?
No, it's not moving to this side.
So the ball is still moving in a plane, like 2D.
Okay.
It's not like the ball is moving forward and back and up at the same time.
Okay.
The ball is basically moving in like a parabola.
Would that be like a curveball? That was 3D?
Yeah, curveball. Now it's now it might be going up and curving and down at the same time. Yeah.
This is just if it was line drive?
Yeah, this is just the ball is just literally, if you look at it from the side, it's just kind of going like this. It's not moving in and out. If it were, that complicates things a little bit. Okay, so any question on how we got those vectors? All right, so that's part 2. Okay, so there is one question I need to change. See, I might have already changed it because it looks like I erased something. Okay, did I put 66? No, I got rid of 66. So, yep, that's it. 25 to 47 and 55 and 57. Okay, on the 25 to 47, just odds. Okay, just odds.